We're gonna burn through the normal first day stuff and then get into it. What you're looking at right now is the bulletin board for the course on My Notre Dame. This looks pretty identical to what we did, or how I had things set up last year. I think everybody had trig and pre-calc with me last year, so it all looks the same. I'll put the links to the class videos in the spot and the archived agendas and all that stuff, and we'll work a lot through OneNote, same way as we've done in the past. Everybody cool? Okay. Syllabus link is there on the page. Syllabus is here that we're looking at. Course breakdown, so 10% or 50% from the test, 10% homework quiz, 25% homework, 15% exam. So you notice that some of these percentages spread out a little bit from last year. I moved some stuff around because we're going to emphasize some other stuffs. Since an AP course, 90% or better both semesters get you the fancy certificate in your packet at graduation. So homework is going to be a little bit different this year. We're still going to have a weekly problem set, so due Sunday at midnight, just like we had last year. But we're also going to have some dailies as well. So these daily assignments are going to be multiple choice practice questions, like former AP test multiple choice practice questions, and they're going to be run through the AP Central. These assignments are going to be due the same day they're assigned and are going to be graded for correctness. So it'll be pooled in with the homework grade. So the problem sets will count as completion credit, just like they always have been. These ones will be for correctness. It's never going to be long. It'll be like 5 questions or something. And they're just points, right? Just more points. Okay? Will we do that every day? No, probably not. But, every week or so we'll do some. Again, for those of you who don't know, I think everybody's required to take the AP test at the end. The AP Calculus exam contains 4 sections. There's a multiple choice section with calculator, without calculator, and then a free response check section with calculator and without calculator. Don't freak out about the without calculator parts because the questions are worded in a way that the calculator would not help you anyways. So it'll be fine. And we're going to do lots of practice on these things as we go throughout the year. Part of the point of doing the multiple choice questions is to just get practice, because when was the last time you took a multiple choice math test? Yeah, like maybe a last AP test, maybe you say like the ACT or SAT.
Oh yeah.
But like in a classroom, it's been a long time, right? So get some practice going on those. Late assignments, we're going to be a little bit pickier about this year. So we're going to start marking things late. I would say that the first month or so, I'm going to be pretty generous about not marking things late for sync reasons. So if you have something where it gets marked missing or partially correct or partially missing, and you realize what happened and you just email me that same week and fix it, it's fine, right? So, like you turn the stuff in Sunday at midnight, I grade it Monday or Tuesday. You notice that, oh, shoot, I did this and I didn't get my credit for it. Just resync things, send me an email. It'll be fine, for the first month or so. After a while, though, like the second year we've done this, so we should be getting good at it by now, right? Not an unreasonable expectation. So the homework quizzes, again, in preparation for what we're going to be doing for the AP exam, are going to kind of come in 2 types. So they're going to be free response with or without calculator. So this would be something you do on paper in class. Or the second would be multiple choice without the calculator. Again, would be something we do in class, but on the computer rather than with a paper and pencil. And again, we'll give you similar kinds of unannounced, but still some kind of something's going to happen this week warning like we did last year with Sophia.
Can we get
partial credit for multiple choice by showing work, or is it?
It's going to be all or none. But it'll be like, instead of having like 3 questions, it'll be like 10.
Right.
Because they should be quick. They're going to be relatively, or 5 or something, where it's like, it's not unreasonable, and we'll see how things are going, and if it becomes like, this seems like a poor grading setup, we can readjust. But again, this is only 10% now.
Right.
The homework quizzes are much less weight than they were before. So I moved some things around because it seems more fair, right? Or a better representation of what you guys can do. Tests will still be the same way. If you're somebody that needs the extended time for your tests and stuff, get on that. Let me know. And we'll run that through counseling. All I ask is usually that's done in a single sitting. So it's not like, I'm going to do 45 minutes here and then like 45 minutes there and like a half an hour after school, just like in one block, please. You guys are seniors, so you know about dress code and how to use your computer and academic honesty. All that stuff is basically copied right out of the handbook. So gonna buzz through that. Absences, same way as last year. If you miss a homework quiz, come during community time. We can do it during community time. If you miss a test or whatever, just study hall or testing room is probably your only 2 options. Get with me within a week to schedule something. You don't have to have it done in a week, but you should tell me what your plan is within a week. Again, at the end of the semester, we're going to drop a homework quiz, drop a homework grade, and then you'll have the doubled high test or retake option capped at 85%. Semester 1, we're going to plan on covering chapters 2 through 4, and then second semester is chapters 5 through 8 with maybe some portions of 9, 10, 11, time permitting. That's the plan. This syllabus is, again, on the bulletin board. And just like we've done in the past, we're going to do the syllabus sign-in sheet. So if you look at the last page of the syllabus, it's the same sheet as you guys saw last year. I also have if you're a paper person, you can just print the single syllabus sheet without having to print the entire syllabus. There's a link to that. To download on the My Notre Dame page, or you can just dump it into OneNote and do it in OneNote, which is perfectly fine also, like we've done before, right? You guys kind of remember last year? Okay. Let's go and set up our OneNotes. We're still going to use OneNote rather exclusively for the class. So fire up your tablets. Open up Microsoft Teams. If you don't remember where that is on your computer, the easiest way to get to it is just press the magnifying glass and then type in Teams in the search bar, and it should pop right up. I'll give you guys a second to get your tablets booted up and going and pull up Microsoft Teams. It takes a minute for that stuff to open. I understand.
How did it get worse though?
They wanted to kick our phones off. They kicked the tablets off too. So.
Well, part of it is that, are you on the guest or the student?
Student.
Okay. Well, good. That's a start.
Yeah.
Okay.
Yeah,
okay.
It's not good.
Okay. Well, we'll be patient here. It's okay. It's always bad on the first couple of days because everybody's doing the same thing, and it is all really heavy on, data usage or whatever. Opening Microsoft Teams. And on the sidebar of Microsoft Teams, you'll want to click on the Teams option, and you should see yourself or your class already preloaded as 5th hour AP Calculus as one of your teams. I set that up previously this week. Does anybody not have a 5th hour AP Calculus team? Or is anybody still working on getting there? Great. So go ahead and click that 5th hour AP Calculus team. From there, in this middle pane, you'd want to find the class notebook. Click on that. You're going to see at that point OneNote starts loading into that pane on the right. From the options at the top here in the OneNote, you'd want to find the Open in Browser option and pick instead Open in Desktop. And that'll should open OneNote for you automatically and load in your shared notebook. And we're done. And you guys have done this before for me, so I hope this went rather smoothly. I'm not going to walk by and double check anything. I'm going to trust that you guys are comfortable enough with me that, like, okay, you lost me there, you know, or that you got it figured out because, yep, perfect. Yeah, it takes a minute to load everything in. It didn't take any time for mine because I already loaded all my stuff in like 2 days ago when I set everything up. But
this just sounds
Should we put the syllabus sign in the homework and go out?
yeah, so that would be the syllabus sign-in is going to be collected as a homework assignment. So you'd inside your name on the shared OneNote, you'd put that in the current homework tab, and that'll be the homework assignment for Sunday at midnight. Realistically, though, Mr. Blick's not looking at anything till Monday. We all know this, right? At the earliest. Sometimes it doesn't even happen on Monday. You know.
Oh, so you're never going to see it again.
yeah, basically.
Current homework. The current homework tab is where...
This is a bad start.
Yeah, that's okay. Let's just recap. I said it quick. Let's say it again. So inside your tab or your section of the shared notebook, there's 3 tabs: current homework, archived homework, notes, and handouts. Current homework is where you put anything that's still waiting to be graded. Archived homework is for things that have already been checked and completed that you want to hang on to. And then notes and handouts are if you're doing notes in OneNote, or you have handouts that I've given and you want to store somewhere so you don't have to keep like arrowing up and then going and finding an arrow back, you know. It just makes it a little bit less jumping around. But don't feel like you have to use any of that stuff. You can just delete out old homework assignments if you're done with them. You don't have to take any notes or store any handouts in OneNote. None of it's required. I just made a space for it in case you wanted it. Everybody happy here with OneNotes? We should be fairly comfortable using this as we did it a lot the last year or two, depending on how long you've had me. All right.
Wait, you're still filming lectures, right?
I'm doing it right now.
Fantastic. So I won't fail.
No, you should not.
That is so false.
All right. With your tablet, can you open up the My Notre Dame? Go to the bulletin board for this class, and we're going to get you guys all registered through the myAP, which is where we're going to do the online multiple choice practice questions. Amongst other things I can do with it, but we're going to start with just kind of using that as a practice. So if you click on that link to myAP, you should hit student, and then you'll create an account. And kind of go through that. Eventually, it's going to ask you for a code. The code for this class is this one up here. So when you get to that point in the registration process and you need the code to join, this is the code that you'll need. I haven't seen what it looks like from the student end. This is my first year doing it, so it should be relatively straightforward. You're just signing up for something. You know, use your Notre Dame email. And we'll should be good there. I believe so. I believe so.
Can I pull out my phone real quick?
Absolutely, yes. Totally reasonable thing to ask.
It is just so slow.
I understand. I understand. And the AP Classroom, if you've used this before, you know it's kind of like a kind of janky, slow website.
Is this where our, on the AP website, is that where our multiple choice homework will be?
Yeah, so I'm just looking for that right now. Again, I'm getting used to using this as well.
It is so bad. I don't mind it. I've heard of that.
Well, no, you're not in that.
Well,
Yeah, we are both. Actually, no. I just don't.
I just don't like school.
And I think. What is it? Right here? Yeah. So I saw it quite excited for You're lying. I'm not. The part you to be like. Oh, I got honest better, yes.
It's fair, it's fair. What's our schools have got? We need those out.
Those are student.
Is it required or are they just asking for it?
Oh, okay, can I got this?
Oh, sweet.
Oh, I filled that out. Now they have my information.
Is anybody still working on the registration process? Totally fine. We'll take a couple more minutes. I have like a sample multiple choice quiz already queued up for you guys that we're gonna do here real quick. I wrote the question myself. It's one question long. There's no wrong answer. So it's just to,
This is my kind.
I like these. That's a good idea.
it's like just to make sure everything works for me.
Oh, okay.
Yes.
Yes.
So I'm not sure what it looks like on your end. So I'm gonna sneak over here. Who's signed in and already stuff?
I think I was there. So I already
Yeah.
It is on AP.
No, I did. Like I fully like typed that in.
Oh, well, fully.
It came up.
Oh, I like it.
Yeah.
Not gonna load.
Try to find some time for you to do that.
Okay, I'm sorry.
Oh, I see.
Okay. So once you've created your username and your login and you're in to the myAP, you want to go to the AP Classroom link. There's a button there, and then if you look there, there's there's assignments or whatever, my assignments. Go ahead and click that, and you should see one assignment in there for me. Go ahead and open it up and answer.
Is this one the biggest because the exponent multiplies more?
Well, you'd have to think about which one is the most excited. Which of the options is most excited?
Can I do all of them?
Any answer. There's no wrong. I set it up so there's no
Well,
wrong answer.
excited to
This.
the power
I'm
of
gonna do all of
excited. Is excited?
No.
Okay.
Is excited multiply the? Is it one or is it like each letter a number? Like you treat excited as one number, or you treat excited as like
Excited is a.
If it works,
it's like a one side, but it just
okay, got it.
So
We're gonna go with like,
watch
just
it be like three.
the classic.
Oh, I chose the. I know the right answer.
I just
Look,
want to pull it out.
Texas.
That's the problem.
I told, and there is no wrong answer. So go ahead and pick anything and submit.
The right answer. Yeah, you have to do all four.
Oh, you have to pick all four?
Yeah,
Oh, you did do all four.
you have to.
Okay.
You have to pick all four. Yup, you lose.
So did everybody, was everybody able to find the quiz?
1 second.
Okay,
Should be able to.
We get points for that one, right?
sure. I'll mark it in as 1 out of 1.
Oh,
Definitely.
My grade is so high right now.
I don't know. So they get a 0.
I got one.
That's it. You had to select all 4. You had to select
Yeah,
all 4 to
look.
get the.
Yeah, I look. You got it wrong. You had to select all 4.
Oh, you had to select all
Yeah,
four?
you
Oh.
got it wrong.
Good to know about the way I set that up.
That's a
So
0 out of 1 for him.
this is why we're doing this, right? This is the first time Mr. Kulik's setting this stuff up. It's like, I thought that all would have meant that any answer worked, but apparently not.
Oh, I'm the smartest one right now.
So as an aside of these, which one is the most excited?
The last one.
D is correct. What's the next most excited?
That's what I would do.
C. C is the next most.
Based
And
on
then
what?
B. And
Like I didn't know what an exclamation.
sure, yes, assuming that excited is a whole number greater than 1. Yes.
Okay, excited is an imaginary number, so you're all wrong.
Okay. All right.
I mean, I'm the one who got the question right, so you know. I think that makes me
Good. So we're done with that stuff then, right? And we'll do it again. Probably the first time we do one of these in class, we'll do it in class. So if there's trouble finding things and getting it started and all that, we can troubleshoot that, or at least start it in class. But these are set up so you can do some, take a break, do some, take a break, and it'll save your progress. Sophia,
What's the exclamation mark called again?
factorial.
Well, I just thought it was an exclamation. Like just an exclamation.
No, this is math class, sir.
Factorial is like multiply 5, then 4, then 2, then 1.
Yes. All right.
Right.
So that's the setup. We got that all taken care of, which is great. We are on to actual calculus content. What? I know. So just as a little aside, calculus can be a difficult class. The hard part, it's not the calculus part, it's the algebra part. It is all the foundational stuff that we've learned to this point you need. So like all the simplifying and like being able to rewrite something in a different way to make the calculus easy, that's the hard part. If you're clever and you're good at algebra, the calculus is pretty easy at this level anyways. If that's a problem, the algebra becomes kind of the big problem. So, calculus invented by or created by? Anybody know?
God.
Okay, we'll say discovered by.
I don't know.
Nobody knows? What? Henry Calculus is not correct, but that's a good guess. So we have two men are credited with the creation. So there's Isaac Newton. And then Gottfried Leibniz. It's German. It's hard to spell. So there was actually quite a controversy at the time as to who the actual author of the technique should be. Newton is the one that got credit in the time, although it's considered now currently that they're authored came up with the same ideas independently of each other. But Newton was more famous, had more connections, and essentially crushed Leibniz, even though he had published first. So, in the hindsight, Newton, not a nice guy, at least professionally. So, what was Newton famous for? Gravity, right? That should be the first thing that you think of when you think of Newton. He was the one that described, or at least our initial description of gravity. I mean, that description was refined later by Einstein to be more accurate or more general. But Newton was interested in describing gravity, right? How that works. What's the famous story about Newton? The apple fell on his head while he's sitting under the tree, right? So what Newton was really interested in doing, you have Newton sitting under the tree, and then you have like the apple falling on his head, right? It's good artwork. He's sitting down. That's his waist, right? How do you sit?
Oh my God.
Everybody's a critic.
Yeah.
Everybody's a critic. Good gravy. All right. Are you happy now? Okay. Do I have to color the tree?
Yeah.
Be nice.
Get out of here. We're not doing that.
Well, you do have like different colors. But what do you think?
I do have different colors to work with, but I'm not doing it. I'm not establishing that as a precedent that Mr. Kulik's going to color
If
things.
something's worth doing, it's worth doing it right. So.
This is right enough. Okay. It ain't wrong. All right. So the question that Newton had is, how fast is that apple falling, like in that instant? So it'd be relatively easy to figure out the apple's average speed by taking the distance that the apple fell and dividing it by the time it took, right? There's a mosquito flying around in here. Right? If you want the average speed, you just take the distance traveled and divide it by the time it took. But what do we notice about things that are falling? Are they going the same speed the entire time?
No.
Yeah, they're getting faster as they fall, at least to a point. For those of you that have done physics, know that there's a speed at which, at least on Earth, things stop speeding up. That's called terminal velocity, yes. It's when the air resistance cancels out the force of gravity. If you're in a vacuum, there is no terminal velocity because there's no air. All right. So what did Newton do? Well, that's what we're going to work on developing here in this first chapter, is how to solve this problem of trying to figure out going from an average speed to trying to get an instantaneous speed. That's going to be the goal here in this first chapter, is how in the world did he come up with how to do that? Okay? So that's just like a motivating question to kind of keep in mind what we're about to be doing. All right, so the first thing we want to do is talk about tangent lines. Anybody remember what a tangent line is from geometry? Okay, that's okay. Was it 3 years ago for most of us, or more? Or never?
Yeah.
Robbie?
It's like a line going like straight from a point in a circle.
Great. Absolutely, yes. A tangent line is a line that intersects the circle exactly once. So if we have some circle here, hey, that's not so bad.
It's a good circle.
And that guy would be our tangent, or would be called a tangent. Okay? Does that ring a bell? Or you're okay with like, okay, that's what it is. I'm okay with that. Sure, easy enough. So what we want to do is we want to extend this idea. So this is like a tangent to a circle. What if we want a tangent to, say, a function? So what is that going to look like? So let's say we just have some function that looks like this, and we want to draw a tangent to that function, say like at this point right here. We'll call this point P. So that tangent would look like this. It's not intersecting the function exactly once, but it should be exactly once in the neighborhood of that point P. So in the local area around P, it should intersect it exactly once. Is it okay that it intersects the function again way over here? Sure, but you should be able to find like a small enough region around P that it only intersects once. Everybody's okay with that? To describe that tangent line P, what am I going to need? So if I want to write an equation for that tangent line P, what am I going to need? The slope, right? What is going to be the same as the slope of the tangent line? So how could I figure out the slope of that tangent line? I know nothing else about the tangent line other than it's intersecting this function at the point P. So what I need then is, well, kind of. What we're going to do is we're going to use our function and try to find the slope of that function at the point P. Because the slope of our function at P should be then the same as the slope of our tangent line. Now, can we find the slope at a single point? No. That's a problem, right? So what are we going to do? We're going to take 2 points and get them closer and closer and closer together and see if that slope converges to some value. Okay? So let's look at a specific example of doing that. Everybody's okay? Let's use, oops. Now that's, all right. So let's just say that we have the function f of x equals x squared. And let's say that we have our point P at the point 1, 1. That probably doesn't really look like 1, 1 though, does it? I can probably do a better job on that. That probably looks a little bit more like 1, 1. It doesn't really matter though, guys, right? So what I'm going to do then is we'll find another point Q on this function. And we'll find points Q that get progressively closer to P. So maybe we'll start with Q is 2, 4. And then maybe 1.5, comma 2.25. How am I getting the y coordinates out of this? How's Mr. Kulik doing that? Yeah, I'm just plugging it into the function, right? 1.5 squared is 2.25. Everybody's still doing okay there. Maybe we'll do 1.25, and that is 1.5625, and then maybe we'll do 1.1, 1.21. So we're just getting kind of progressively closer and closer to P. Everybody's cool? So then, using that, we can calculate the slope for PQ by doing rise over run. That's with 2, 4. That one is 2.5. That is 2.25. And then my last one, I forgot to write down the answer for this apparently. So just one moment while I type that into the old graphing calculator. 2.1. So what is it that it appears that this slope is approaching? Seems like 2, right? So what mathematical operation did we just do by doing this? We have a name for this. We used it last year in trig and pre-calc specifically. What did we just do here? We took a limit, right? This is the limit as Q approaches P of the slope of MQ right? Is that what we did? Yeah? Now we can formalize that a little bit better by inputting using our variables, right? So this is also the same as saying the limit as x approaches 1 of x squared, that's the y coordinate for f of x, minus 1, that's the y coordinate at P, over x, that's the x coordinate for f of x, minus 1, that's the x coordinate at P. Let's just kind of label that. Right, just if you look at that again, it's sometimes unclear, like where did the x squared and the 1 and the x, where's these things coming from? Everybody's cool? Okay. So this is something that we could then do on our calculator, right? Like we did last year when we took limits with our calculator. So notice what have we really been trying to do here? We took like a geometric question and tried to turn it into an algebraic expression where we're just going to take the limit of that expression, right? Take something that was geometric and turn it into something that was algebraic. And then what did we like to do last year? We did this y-vars thing as we're approaching 1, right? So we did like 2, and then we did like 1.5. Oops, forgot a decimal in there. And we do like 1.1. We do like 1.01. And it was nice to do this because it was just easy to edit, right? So we're getting closer and closer to 2. We'll do this again from the other side though, right? So we should do this from 0 and then like 0.5, 0.9, etc. Because we need that limit to agree from both directions. So it looks pretty good to me, right? Like this is going to 2. You guys all remember doing that last year? It's kind of a hassle.
Wait, how do you get the Y1?
The Y1? Sure, we can do that again. So what I did is I pressed vars, and then I go over to the Y-vars, and I pick the function option, and it's the first one on the list. Yeah, of course. And as we go, we're going to develop ways to do limits that are better than creating a table and plugging it into our calculator. Okay, but that is a legitimate way of evaluating a limit. Legitimate way. Has some downside to it, but there's nothing wrong with doing it that way. So we get that this is 2. So then our tangent line, if we want to write the equation for this, I'm going to use the point slope equation of a line. Oops. Just call it x and y. So we have y minus the y coordinate for p equals the slope times x minus the x coordinate p. Or when I rearrange this, I just get y equals 2x minus 1. Mackenzie. Was going to be the slope. So I got it from evaluating this limit with my calculator, right? I saw that if it were approaching 1 from below, I got 1.999. And when I approached 1 from above, I got 2.01. So seems like 2 is the value for that limit. Does that feel okay? That's what I was doing on the calculator, was just to kind of justify what we kind of observed, before when we started doing this naively. And then I pointed out that, hey, what we're really doing is taking a limit. And there we go. Okay. So far, so good. So we've talked about a tangent line to a curve. And to write the equation for the tangent line for a curve, we need to find the slope at that given point. And the way we're going to do that is using our limit to evaluate like a slope equation, right? Do we need to do another, or do you guys think that's okay? It's okay? All right. All right. So, who can tell me the definition of a limit? That's great, because we never gave you the formal definition of a limit at any point prior to this. I'm going to write this down right now, and then you can immediately forget it, because it is beyond the scope for this class. But this is what the formal definition of a limit is. I'll explain to you afterwards kind of like intuitively what this is saying. All right. This is also referred to as the epsilon delta definition of a limit. So what we're saying is let f of x be a function on an interval containing the value a. Then the limit as x approaches a of f of x is equal to L if for every number epsilon there exists some number delta such that if the distance between x and a is between 0 and delta, then the distance between f of x and L is smaller than epsilon. What in God's name is this really saying? Let's draw a picture, because intuitively with a picture it's like, all right, yeah, sure, that's fine. That makes sense. That's what a limit would need to do. So let's say here's our xy axis. Oops, that doesn't really look very functioning. Say there's our function. And let's say this is our value a. And so this would be like our value L. What we're saying is that if I look at this region around A, I should be able to find a region around L also, and that as I shrink down that value for delta and gets closer and closer to A, I'm going to be shrinking down that value for epsilon, getting closer and closer to L. So all we're saying is that as you squeeze in closer to the desired x value, you squeeze down so you're getting closer to the value of the limit. That's all we're really saying with this epsilon delta definition. Very technical. We're never going to use it in this class. It's beyond the scope of this class. But that's really what we're saying formally for a limit. Sure. So it's just kind of saying that as we squeeze down this value of delta so that that boundary is getting closer and closer to A, it's also squeezing down this value of epsilon, so that's getting closer and closer to the value for L.
So as delta gets closer to A, epsilon gets closer to L.
I would say as delta is getting smaller, epsilon is getting smaller as well, in that they both can, once you've converged at A, you should be converging at L. Yeah, that's all we're really saying. And the reason it's worded this way and defined this way is that you can actually, with this formulation, you can prove things are the limit. And it's not something we're going to do in this class, but if you're like planning on being an engineer and you're doing like Calc 2, Calc 3, at one point you're going to do epsilon delta proofs, and we're going to use this definition to show that something is a limit. That's something that you would do. We're not going to do that in this course, but
Do we do this class?
yeah, we show stuff, like show that, you know, blah, blah, blah is that,
Like,
which is
you'll
kind of
show
like a
us, but
proof.
It's not going to be questioned.
Yeah, I mean, not kind of-ish,
Just say
kind of-ish.
You'll make it feel like I say no.
Oh, no, then, no. Okay. So, let's look at evaluating some limits. So we're just going to do some practices. We have two ways to do this, to evaluate a limit. What are the two ways that we know how to use or how to do? We can use a table, right? Like we just look at some values. And the other way would be to look at a picture of the graph, right? So, just to kind of reiterate that, if we go back and we look at the picture of this graph, and we look at the value for 1, it looks like that value is 2, right? Which is what the limit was in that previous example. Why can't I just do like, oh, what is the, if I just plug 1 in for x, why don't I just get 2 back out of that? Look at the function. What happens if I plug 1 in? I have 0 over 0, right? If I zoomed in really, really closely to that picture, you'd see there'd be a gap at x equals 1. There's an open circle. There's a removable discontinuity there. Okay? So we can't like just plug the number in, but if we look at the graph, oftentimes we can just tell by looking at the picture, which is the best way of doing it, right? Because it doesn't require a bunch of calculations. It just look at the picture and see what it looks like, which is not bad. All right. So let's just do a couple of practices. Pull out your calculator. We're just going to ask you guys to do the same thing, see if we can come up with the same limits. You can do a table or a graph or either one. Totally fine. I have done all of these in advance. Can anybody do this one, take a guess at this one without actually doing it in their calculator based on what we just did? What was that, Nico? It's not 1. 1 over 2 is going to be the answer. Remember, this is just the reciprocal of the previous function we did as x approached the same value. Right? We did x squared minus 1 over x minus 1 in the previous example. Here it's just the reciprocal. Would stand to reason it's probably going to just be the reciprocal limit. But put in your calculator. Take a look at the graph. Do it in the table. See if it matches. When you track up from 1 and track over to y, does it look like it's a half? So if we type this in, oops, you goober. Okay, so here's my function. If I look at x equals 1 and I track over, looks like a half. Right? Or alternatively, I can plug in some values. So let's see what 0.99 looks like. Very close. And then see if we can see what a little bit above looks like. Looks like a half, right? Everybody feel okay on that? Let's try another, right? Again, do it yourself on the calculator. Good practice. Now note that what we're seeing here, or are we actually, with using a table or using the graph, are we actually ever knowing that the limit is what we say it is? Do we know it to be true? No, we're just kind of making a really good guess. And oftentimes that's good enough, right? To prove that that is actually the limit, we'd have to do something else. We'd have to use the epsilon delta proof or use some other theorems that we'll build out here a little later, because we're never going to do an epsilon delta proof in this class, but we will build out some theorems to help us evaluate limits like these and know the answers exactly whatever. But you're almost never going to be wrong if you're using a graph and a table to look at a limit. So try this one. Again, notice what happens if you just try to plug in 0. Something over 0, right? So You can't just plug in 0 to get the answer. You have to either look at the graph or build a table out.
It says invalid dimension.
Okay, so it's probably good. When you look at your y equals, is plot 1, 2, or 3 highlighted? So move your cursor up there and press enter so it's not highlighted, and then try pressing graph again. Did that fix it?
Yeah, but
Yeah, it's the slope just 1.
I got 1/6 when I did this.
Wait, no. Is mine just a straight and flat across that axis?
Okay, well let's type it in together, right? So I like to use the fraction command. You guys all remember how to get the fraction bar? Alpha y equals, and then the first option. On a problem like this, that's going to be really helpful. And then I have to make sure that I'm going outside of the radical. Okay. So I've typed her in. And then if I hit graph, I'm looking at x equals 0. So it looks like it's way less than 1, less than a half. To come up with 1/6, though, it's probably going to be a situation where doing the table is super helpful. And I know 1.6 repeating is 1/6. So
wait, can you just trace the points?
you could, yeah, but you're not going to have, if you try to put in x equals 0, you just get nothing because it's undefined at that point, right?
Wait, why
But
would we undefined?
if I plug 0 in for x, I get something over 0, right?
I mean, like, just put your cursor on.
Yes, you can do the trace. Yeah, that certainly works for sure, Paul. Okay, Sergio.
Probably a stupid question, but how do you know to like type in 0.99 for x every time?
Oh, shoot. I wasn't supposed to be doing that. I was supposed to be doing close to 0, right?
Yeah.
Thank you. Yes. 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 Excellent. Thank you. So I should have been doing like 0.01 and then negative 0.01. Yes, thank you. All of you guys that were like raising your hands and were like, what the heck are you doing right now? Thank you. Thank you. Interrupt me if you see me making a stupid mistake. Taylor, what's up? Come show me.
okay, that is so. This is what I plugged in.
Okay, so the errors from this. So if we unhighlight that, we should be good. Okay. Except mine was a plus 9 and not a -9, so that's why your graph looked different.
Yeah.
And now you have like the
I
same.
think now.
There you go.
Okay. Alright, thank you.
No problem. No, I made a mistake. So, Victoria, if you look, this is now above 0 and below 0. So, yes. Let's try another. The limit as x approaches 0 of sine x over x.
This is the first time I've known what's going on.
I think in a way, this should be easier to kind of keep track of what's going on because we're really starting from zero. Everybody's from the same spot where it's like,
Last year was like the integrated kids.
yeah, nobody has a big head start here. So when you graph this one, because there's a sine function in there, what do you need to do first? Or what do you need to make sure? What mode should you be in? Radians.
I feel as if my calculator probably
Wait, how do we know which one?
There's a trig function you're graphing.
Right.
So radian. So from looking at immediately, you can tell that the limit should be. So you're looking at x equals 0. So it looks like 1 is the y coordinate. That's it. I'm just looking for the y coordinate.
Your cosine would be 0, right?
Cosine, that would be a great question. That's cosine of x over x.
Okay, so it's 1.
Will be a big problem.
Yeah.
That maybe does not exist.
Yeah. Probably. I was like waiting for the graph.
Is everybody feeling okay doing these? I have a couple more. So next one we're going to do is sine of pi over x.
We're using radians still, right?
Yes.
Pi.
100%. Anytime you're doing graphing with a trig function, it's radians.
Is there ever like a time we're gonna need to switch to degrees for this?
For this class?
No, for just for this.
No.
So keep it in radians.
Yeah. And maybe at points in this class, perhaps, but not anytime soon.
They should just like find a way to combine this.
All right.
Well, it's a different number.
What's that?
If you're
But there's some pictures.
What's
the limit?
The limit. Oh, thank you, Mackenzie. Yes, let's write it down.
Wait, what are we writing? Wow.
The question.
I mean, is that ever going to be like a different way, like different outcome of doing it? If that makes sense, by that doesn't make sense. But it's the same process every time, right?
Well, I mean, it is right now.
Yeah.
It will be for a while.
Okay. Yeah, I like it.
What do you? Here's the graph.
Right. Scary graph.
Well, let's look at the table.
Oh wait, I have to do that. Let's do 0.
So you guys all think 0?
I know it's a curveball. I don't do very well, but I think it's
Wait a
0.
minute.
0 is not the answer.
Wait. It should be.
There, it's undefined.
It's. You'd say for limits, you say does not exist.
So why? Why?
So great. Yes.
It's possible 0 points, right?
Okay.
Oh, okay, got it.
Okay. So when we take, so if you plug in 0, you're taking sine of undefined, right? So that's undefined, period. If I do pi, or I'm sorry, okay, where is the sine function equal to 0? So think back to the unit circle. When is sine 0?
Oh, it's.
At 0 and pi and 2 pi. Every whole number multiple of pi is 0. What is pi over 0.01? That's 10 pi.
So he's right.
I'm not wrong.
Which is evaluating to 0, right?
Oh, so.
Oh, I am wrong.
So we would need like somehow getting like a
Just don't put this one on.
nope, this is absolutely something that would pop up on an AP exam.
Oh, really?
Yeah.
Okay.
So let's do something like, instead of doing, let's do like 2/7. Right? Like, and as you do, try doing like negative 2/7. And then you do say something like, okay, maybe let's do something smaller. So maybe negative 2/9. You need to be something though that's not going to be something that, but I need something that's not a fraction over 1. Like 1/3 or 1/10 or 1/9. All those are going to zero out because all of them are going to or simplify to a whole number multiple of pi.
But in that case, does that always mean it does not exist? When something like with 1 always simplifies to 0?
No. Because if we had evaluated x equals,
Okay,
this to be 1,
Right.
then it's no problem.
But if it is approaching 0,
Well, it's if plugging it in gives you undefined, right? If I try to plug 1, if I just had x approaching 1, I could just plug 1 in, right? Sine of pi over 1 is just 0, so that the limit there is 0.
Do you ever get zeros more than?
Sure. Yeah. So the graph is the better one to look at here, and I would zoom in closer here to take a peep. So if I zoom in even closer than that, oh, sorry, positive. And then I need, sorry, it's 0.1 to positive 0.1. Like, see how I keep zooming in and it's still like erratic, like you're not getting anything that's like smoothly looks like it's going to a single point. That's my better indicator that this is going to be a does not exist.
So then if your limit is x approaching 0 and you have like in the table an error at 0, do you know then that it does not exist? If your limit is approaching 0?
No.
So that
Still doesn't tell. You literally have to be looking at the graph and going like every time I zoom in and get closer and closer and closer, it's still just like a mess of erratic behavior.
So that's the only way you know.
That would be the table is not going to be on a problem like this. The table is going to be deceiving.
So that's
And when I'm zooming closer and closer in, I'm not getting any closer and closer to settling down to a value. Now, this erratic behavior, when can this happen? I only can get this kind of bonkers behavior if I'm using a trig function, right? A trig function. This could not happen with like a polynomial or a rational function or something else. This erratic kind of behavior can only happen with the stuff we know about with sine or a cosine or a tangent or something.
And then can you have a does not exist for a function that doesn't include the
Sure. I could drop the pi out of that and still, yeah, the pi is in there just to make, if I drop the pi out of there, it's still going to be does not exist. The reason the pi is in there is because it really makes the table deceptive to you. If I dump the pi, then the table is no longer deceptive.
Wait, so but it will only be non-exist if there's a trig function.
No, that's also not correct.
Okay.
But you're only going to get like crazy erratic behavior like this if it's a trig function.
And then if it wasn't a trig function and you don't have the crazy behavior, how do you know that doesn't exist?
We'll talk about it. It's coming. It was to be done in the end of this section, but we ran out of time, so it's fine.
Is there not homework?